Marcus Webb was 54 years old when his position as construction site supervisor disappeared with the contracts that had sustained it. 17 years of reading load specs, cold weather framing requirements, and structural failure reports. The layoffs came regardless. His savings held for 8 months. Then the apartment lease ended. What remained was a 1.2-acre parcel in Geauga County, Ohio. His father's land, clear title, taxes paid current, no utilities, no structure. In late September, he ordered a mini Quonset kit from a Midwest agricultural supplier, corrugated galvanized steel panels on a freight pallet. Total remaining budget, $650. He had built structures for 22 years. He did not yet know which 3 failure modes a sustained Lake Erie blizzard introduces that no standard build manual addresses. By the second week of September, Marcus was at the Geauga County Public Library pulling USDA cold weather shelter documentation and agricultural building literature. A legal pad divided into 2 columns. Options on the left, failure modes on the right. Used travel trailers ran $2,800 to $6,000. Prefab tent structure started at $900 before anchoring hardware. A wood frame lean-to carried permit exposure and required more construction time than the forecast allowed. Every option crossed off for the same reasons: structural integrity under 24 inches of wet snow, thermal performance below 15 degrees Fahrenheit for consecutive nights, moisture management across sustained event without a drying interval. The mini Quonset emerged from military logistics literature, not survival forums. The arch geometry distributes snow load along the radius toward the base rather than straight down, an engineering principle developed from a Nissen hut design used in both World Wars. Marcus found an 8 by 12-foot galvanized steel kit for $389 from a Midwest agricultural supplier. Remaining budget after the kit, $261. He did not yet know how many problems that $261 had solved. Gerald, a 67-year-old retired plumber from the adjacent property, walked the parcel in early October and looked at the stacked panels. He said a metal arch in a real Lake Erie blizzard was a fancy tent. Add insulation, get a propane heater, put plywood on the exterior if wind picked up. Marcus heard him out. He did not argue. Gerald's logic was not wrong. It was incomplete, because it treated 3 distinct threats as one problem and prescribed one response. Most people facing a winter metal build focus immediately on what goes inside. More insulation, bigger heat source, thicker bedding. That logic fails not because it is wrong in isolation, but because it ignores 3 mechanics blizzard conditions introduce that ordinary cold nights do not. Threat 1. Wet snow load on an unanchored arch base opens gaps of the panel joints that no wall insulation above them compensates for. Threat 2. A metal shell generates a condensation cycle across consecutive nights that degrades insulation from inside without visible warning. Threat 3. Ground infiltration through an unsealed base perimeter drops floor temperature independently of everything the walls are doing. 3 threats, 3 methods. None of them involved adding more insulation to the walls. Consider 18 inches of wet Lake Erie effect snow across an 8-foot arch span. Wet snow runs 20 to 40 pounds per cubic foot. 1 linear foot of accumulation transfers 160 to 320 pounds of lateral thrust toward the base of the structure. Most people think about the weight pressing down. That is not where the arch fails. Load travels along the arch radius, the design structural advantage, and concentrates at one specific point the assembly instructions do not emphasize, the joint where the arch foot meets the ground sill. Structural engineers call this base shear. The original World War II Quonset design addressed it with driven anchor stakes and continuous sill bolting. Specifications documented in declassified military engineering records through the National Archives digital collection. The civilian mini kit does not include that engineering. It assumes level, compacted ground, and an operator who reads the anchoring section carefully. Many do not. An unanchored base sill, under repeated lateral snow load, rocks the panel foot incrementally, opening a gap of 1/2 inch to 1.5 inches at the base joint. On a night when outside air reads 4 degrees Fahrenheit, a 1-inch gap drops interior floor temperature by 8 to 14 degrees Fahrenheit, regardless of what the walls above it are doing. The insulation above it becomes irrelevant. October 22nd. Ground temperature at 6 inches, 38 degrees Fahrenheit. A 2-week window before the frost line dropped below practical anchoring depth. The first method is called the base anchor protocol. 8 galvanized ground auger anchors, 10-inch minimum shaft, 16 self-tapping hex bolts, 1 tube of construction adhesive rated to negative 20 degrees Fahrenheit. Anchor points every 24 inches along both base sills, driven to soil resistance rather than a torque spec, because resistance is the honest measure when ground density varies. Adhesive bead along the interior base joint before final panel seating. Closed cell foam backer rod pressed into the exterior base joint to seal micro gaps the bolt pattern cannot close. The same material used in commercial HVAC exterior wall penetrations. Marcus tested the completed assembly by pressing both hands flat against the arch panel at mid-height and pushing with full weight. No movement. A builder in Youngstown who documents an off-grid homestead operation found a 3/4-inch gap at his own base joint on night 4 of a January cold snap. After 2 nights of adding blankets and getting colder, he found it with a flashlight at 2 a.m. The gap had opened across 3 storm cycles without any visible sign. Total cost for the base anchor protocol, $38 to $44. The first thing Marcus upgraded was not what was inside the structure. It was where the structure met the ground. Marcus woke on night 3 at 3:20 a.m. The sleeping bag shell felt heavy in a way it had not on night 1. Not wet, heavy. He lay still for a moment before moving. Then he ran a hand along the interior arch panel above him. Not droplets. A continuous film. The way the inside of a cold soda can feel the moment you pull it from a refrigerator. He pressed his palm flat against the steel. It was at refrigerator temperature. Not close to it. Exactly it. The thermometer on the interior wall read 34 degrees Fahrenheit. Outside ambient, 8 degrees Fahrenheit. He pressed the sleeping bag shell. The loft had compressed noticeably. On night 1 it had resistance. Now it flattened easily under his hand. One person sleeping in a sealed space exhales approximately 1 liter of moisture over 8 hours. In a wood frame structure, some of that moisture migrates outward through panel gaps before reaching condensation point. In a sealed metal shell, galvanized steel conducts heat 300 to 400 times faster than wood framing. The interior surface reaches near ambient temperature within 40 to 60 minutes of any heat source cycling off. Dew point is reached on every cold steel surface simultaneously. The moisture has nowhere to go. A 0-degree F-rated synthetic sleeping bag can lose 40 to 70% of its insulating capacity across 3 consecutive damp nights. It does not announce this. The bag still looks the same. It still feels warm for the first hour. It fails quietly across hours while the person inside adjusts and adds layers and cannot explain why the cold keeps arriving earlier each night. The second method is called the thermal decoupling layer. It does not add insulation to the metal. It removes the metal from the thermal equation entirely. The material is foil-faced polyester board, 1.5-inch thickness, R, 10 per inch, cut to fit each interior arch panel section and friction fitted against the steel, leaving a deliberate 3/4-inch air gap between the foil face and the metal surface. Most builders focus on what to put against the cold surface. The thermal decoupling layer ignores the cold surface. Still air carries an R value of approximately 1 per inch. The gap prevents direct conductive contact between the warm interior air and the steel. The foam face never drops to the dew point of the interior air. The condensation cycle stops because there is no longer a cold enough surface for it to collect on. Building scientists call this thermal decoupling, the principle underlying every modern cold storage facility and commercial freezer wall assembly. Total interior lining cost for an 8 by 12 foot structure, $80 to $110. The complete cut sheet reference is in the mini shelter build guide, linked in the description. Code shelter brings it to $19. The third method is a vapor barrier floor. 6 mil poly sheeting across the entire ground footprint, lapped 6 inches up the base panel interior. Without it, ground moisture migrates upward to the soil continuously, adding to the condensation load from below, while the decoupling layer manages it from above. Cost $12 to $18. One additional element applies to any combustion heater used inside. A propane unit in a sealed metal shell under 100 cubic feet produces CO concentration faster than in larger spaces. An emergency management specialist consulting on cold weather shelter documented dangerous concentration levels within 8 minutes of exhaust restriction in a structure this size. 1-inch ventilation gap at the door base when the heater runs. Carbon monoxide detector at sleeping height, $15. Not optional. The three methods do not operate independently. The base anchor protocol holds a thermal envelope closed. The thermal decoupling layer keeps it functional across consecutive nights. The vapor barrier floor keeps the ground from undermining both. Miss any one, and the other two cannot compensate. November 17th through 24th. 7 consecutive nights. Ambient lows of 4 degrees Fahrenheit to 11 degrees Fahrenheit. 3 lake effect events. 31 inches cumulative snowfall. Night 1 interior temperature with a Mr. Heater Buddy cycled 20 minutes per hour. 52 degrees Fahrenheit. Night 7. 51 degrees Fahrenheit. Same heater, same cycle, no degradation. Sleeping bag shall dry on morning 7. In dry climate zones, Denver, Albuquerque, the high desert corridor, the vapor barrier floor contributes less. Ground vapor migration is lower, and the gap between interior and exterior humidity is narrower. The base anchor and decoupling layer remain essential regardless. In the Great Lakes corridor, Cleveland, Buffalo, Erie, all three methods are non-negotiable across any stay beyond a single night. Long-term shelter dwellers across the Minneapolis and Western Great Lakes corridor report that even one missed drying interval in the back half of a cold stretch produces measurable sleeping bag degradation by the following morning. The system holds on night 7 the same way it held on night 1 because the moisture does not accumulate. That is not automatic. It is the output of all three methods running together. For anyone tracking the build cost, Quonset kit, $389. Base anchor protocol, $38 to $44. Thermal decoupling layer, $80 to $110. Vapor barrier floor, $12 to $18. CO detector, $15. Total, $534 to $576. Under $650, including the structure, with margin remaining. Marcus survived a November event and a second sustained period in January that held below 10 degrees Fahrenheit for 9 consecutive days. He did not lose the parcel. He did not enter the county shelter system. He did not freeze. Gerald came by in late January, walked the CIR.